oh boy, oh boy, oh boy, oh boy. I got a package from Fluke, and they sent me, well, let's open it together, see what they sent me. So I've been talking with Fluke about trying to find arc faults, or find a method of finding arc faults. And they said, let me send you a little something, see what you can find with it. Oh, he sent me a little note. Have fun testing. Arc faults, as you may know, are notoriously difficult to nail down, find. Inverters will find arc faults, but not really give you much indication of how to track them down or exactly what string they are. Got some stickers, multimeter. Ooh, one of them big old calibration devices. Look at this guy, how cute, he's a little pin. So Fluke sent me this. This is a 345 PQ. It's basically an oscilloscope and a clamp meter. They didn't send me leads in here for voltage testing, but that's okay. I have leads. So I think tomorrow I'm going out to a system which has had sort of on and off arc faults. And we've gone out and done some amount of troubleshooting to it, mixing around strings to try to isolate which strings are the most likely to be bad. But what I'm really curious to see is if you can see like interference in the DC waveform that would suggest potential arc faults. To be honest, I'm not really expecting to find much tomorrow, but I'm bringing you along anyway, just to see what we see. You can see what a DC waveform looks like that's, you know, currently producing in the field. And I don't know, we'll learn this thing together and see what we can find out. Okay, so we're here, finally. A jump scare, dyed my hair again. It's been a couple of weeks. So let me talk about why it's been a couple of weeks. Basically, this inverter is the one that has been giving us arc fault issues over the last couple of months. Now, as soon as I recorded that video, the arc faults on this inverter stopped. Like, they haven't popped up again. Honestly, there's not much that I expect we'll be able to test on this thing. So we're not going to be chasing down a specific arc fault today, but you can see over here, I've been doing a little bit of setup. What I am gonna do is try to at least give us a good baseline of what a DC waveform looks like, and then see if we can cause an arc of our own in order to, I don't know, get views. Also, science. The other unfun thing that I found out as I was plotting to do this video is that this 345 PQ clamp meter is, of course, only 600 volts. And so this system, the one I wanted to test it on, is 1,000 volts nominal. Now, it's not usually up to 1,000 volts, it's usually 1,000 volt max, but it's still usually a healthy 750 to 800 volts when it's running. So I'm gonna need to take one of these strings here and shorten it in the array so we can get down to under 600 volts so that I can safely use this thing and not blow it out. I don't want to blow it out. That's rude to do to a gift from a friend. And you can see there's just a ton of strings plugged in here as well. There are 11 of them, in fact. Really only 10 that are full strings, but I don't need to do anything with the rest of these because there's pairs of MPPTs. So there's one MPPT here for 2 strings. I'm just gonna basically unplug the 9th string from this MPPT down here, hook it up to the clamp meter, as it's already hooked up to my 393 FC, and we're just gonna shorten string 410, and that should give us a place where we can both test voltage and amperage and get the waveform of both, and then we can start messing around with stuff. Now, I think this should be pretty easy because 1, 2, 3, 4, 5, 6, we need to remove 6 of them, so this is the end of this string, which circles back to this one over here. It's 3, 3. This is the one we want to connect our home run into. So I don't think we even need to get a splice wire to go from here to there. I think these will stretch together, which is super handy. Oh man, doesn't even give me much. Come on. Now we should just be able to plug this into this and have nothing bad happen at all. We'll leave this stuff here and go back and take our measurements. We're gonna plug these into our definitely 1,000 volt rated voltmeter first before we try throwing, we gotta turn this on too. All right, we're down to 516 volts, which is where we wanna be. That should be healthily within the range of this thing. So once this starts producing, we'll get a baseline read of what things should look like, and then we'll start playing around. Okie dokie, we do have amperage. We twist that around, it gives us the actual positive amperage. All right, so yeah, so it's saying negative. For the sake of all of our lives, we'll put it around the negative. That way it's much more, you know, AC. Don't know how easy that is to read, but I'll get close-ups in a bit. And we're running at 425 volts. So we'll plug these into here. Man, it is about impossible to get a good, this doesn't have a light up screen or anything, and it's super bright outside. So we're just gonna have to go up really close for observing these measurements. So DC line, obviously, it's a straight line. Now, we're not able to get a lot of detail on that because it's giving us into a range of 600 volts because it's really meant for AC, not for DC. It can see a DC waveform, but it's expecting it to oscillate up and down and up and down, so it's giving us that whole range. Now amperage, the range is a lot smaller because with solar we deal in much higher voltage and lower amperage, so we can use tiny wire. That's why we do things like 1000 volt instead of 600 volt, and why we're moving up to even 1500 volt these days, just not on top of buildings. So I have figured out how to go from voltage and amperage down to just the voltage reading. So there we get a little bit more fidelity in terms of seeing what the voltage looks like. It's still super stable, and the amperage is actually the one that we get the most sort of noise on. I am not, let me be clear, I'm not super experienced in reading oscilloscopes or understanding what waveforms mean. So this is all experimentation, and we're just learning together here. And then this is both of them together. So I have it set up just to make shooting this easier. I have it set up on the positive, and it's going the wrong way through the clamp, so it's all the way in the negative, but we still will get a proper waveform. So let's see what it looks like when we turn the inverter off, right? You saw it bumped up to a higher voltage, and the amperage bumped up, quote unquote, to 0. And if we turn it back on, all right, the voltage lowers a little bit, the amperage goes back down to where I was. It's running about 8 amps right now. There we go. This is, I think, what we want. So this screen is going to capture 50 milliseconds of time, is what it looks like it's doing. Yeah, so we get that on the screen for much longer than we otherwise would. I think we're going to go to next stage of my plan, in which we are actually going to try to create a small arc fault. Now, it's not my intention to go super crazy on this. We're not looking to put anyone or anything in danger. Although any arcs coming from this thing, the way that we're doing them, nothing bad's gonna happen. But I'm gonna disconnect this positive and put my own cable in that line. So what this will mean is I will have my own connector here that's not touching anything that will normally be under production on the roof. And I'm gonna be spacing this out just a little bit to see if we can get at least some buzzing in the connector, something to give us some sort of a, oh, that's interesting on the waveform. Question is, how do I show you what's on the screen at the same time that I'm dealing with this thing? I need more cameras. All right, so we've got voltage, but no amperage yet. We'll wait for it to start up. And then this cable, this is the cable that is our makeshift arc fault creator, potentially. Again, you know, we'll see what happens. So as we wiggle this apart, let's see if we see anything on the waveform happen. Whoa. Yep. Definitely got some arcing on that one. And you know what? We also successfully tripped the arc fault protection on the inverter. So this seems like an extremely good test for an arc fault. Now, to be honest, I was not watching this at all. I'm gonna have to go back in the video. We'll have to see if we can find anything that happened here because I was not watching. I was mainly just, you know, having reasonable panic at the smoke being released. Now this is actually now fused together. Let's see if we can see in there. It is quite toasty, so good sign. That's a good sign that something happened. It does actually still come apart and together again. Now that we broke sort of the initial carbon layer of this connector sort of faulting, it now plugs and unplugs very easily. I'm sure if we were to plug this in, it would work just fine for a little bit until eventually that carbon buildup would continue happening because it's already damaged the metal inside it, and it would eventually arc fault again. My phone is very upset at the heat that I am putting it through today. So I looked at the footage that I got. I didn't see anything obvious from the volts amps waveform. Now, one of the mistakes I made was I didn't have the voltage all the way expanded in the device. And I don't think these things take like recordings of periods of time. So I can't like set it up to record like 10 seconds of something. You can grab a screenshot of the thing basically, but it's old enough it doesn't have any sort of transferring mechanisms to my knowledge. Maybe it does, but nothing that would have video or something like that. So we're gonna try it again. My plug's still okay. It goes in and out all right. We're gonna do it again for science and see if we can get a little bit more fidelity on the PQ, because it would be great if we would be able to see something. It is possible that I'll get back to editing and I'll be able to see better, but it's so hot out here. My phone keeps complaining and dimming and I can't see nothing. So we'll try it once, maybe twice more, and see what we find. Here we go, round 2. Got a little bit of smoke. Oh, I can smell that. There we go, more smoke. That's arcing nicely. Haven't triggered it yet. Nope, now we've triggered it. It's triggered. Honestly, dude, triggering an arc fault with your hands is more with the intention of not stopping it quickly. That raises your heartbeat a lot more than you'd think it does. Egad, despite knowing my gloves are gonna keep my hands safe and they're wrapped around the connector so they'll keep the roof safe, it's not gonna be an arc that gets out of control because it is a finite number of panels. It is only so much power. It's not the same kind of arcing event that you'd get from a switchgear. The DC does hold on to an arc longer because it doesn't have the cycle to break it earlier, but whew, I think that's all I'm gonna do right now. I'm gonna take it back to the editing bay, see what we can see from those two things. Maybe it's nothing. Maybe we'll see, oh, this oscilloscope just doesn't have a high enough fidelity for us to be able to see the intricacies of an arc fault. But it's curious. You gotta be able to see something, right? Plus, it's freaking hot out here. I gotta be done. My phone is done. I'm done. I have a lot of crap to take down off the roof. And so yeah.
Okay, so it's been another couple of weeks. I'm finally back at the editing bay, getting all this sorted out, trying to see what footage I have so that we can figure something out. And one of the first things I did when I got back was to go through the manual for this thing just to see if there's something I might have missed because, you know, internet comments are going to be all over that kind of stuff. Rightfully so. I should know what I'm talking about before I go out in the field. And it turns out that this does have logging capabilities, theoretically. Now, because this was a loaner or sort of I got the impression that this was kind of this is a super old product at this point. They don't make this anymore. I had the feeling that this was probably dug out from behind somebody's desk that's been sitting there for 2-3 years. Whoever knows why it was there, why it got left there. But it turns out I cannot get the logging function on this device to work, not as according to the manual. I can turn it on. You're supposed to just be able to hit this button once it starts up. If I press record measure, it beeps, but it doesn't actually do anything. Anyway, I'm not an idiot, but it just wasn't working in the field. You are also, again, then able to pull that data off and look at it on an older Windows application for like Windows XP 7, 8. But we don't have any of that, so we're just going based off of the footage that I have. So we have 2 moments to look at in the video. The first one, the glare is pretty bad off of the PQ, but let's pull this up here. I did a little bit of contrast adjustment to see if we can get a little bit closer. And we can go through, we can see the amperage there, we can see the smoke coming out. We are going through, and so here, right where it gets blurry, where we want to see it the most, I think it's actually sort of refreshing there a little bit, but you can see here the amperage jumps up, the voltage jumps up, or the amperage jumps back to 0, rather, and the voltage jumps up. But there's not much fidelity in the little interesting bits. And obviously, if we had the logging capability off of this thing, I would theoretically be able to look at all of this in much greater detail. But it is not to be. That's about the best example of the changeover. We just don't have a lot of information to look at. Now, let's go look for the second one. The second one's more interesting because it is a longer lasting arc fault. The first one happened, and it happened fast, and then it was done. The second one, obviously, took much longer. All right, there's our first smoke. Probably should try to bump the contrast on this one too. Okay, so as we're starting to smoke, you can see the voltage dropping a little bit. Again, right here, we're only seeing voltage in this window. I don't have the amperage up here, which honestly, that's something that I regret. I think we probably are going to get more information on the amperage waveform than we will on the voltage waveform, but hindsight's 2020, right? Also, next time I'll probably bring out a more capable power quality analyzer, but this is where we're at. So we're still arcing. I am smelling the burning at this point, right? That I'm commenting throughout the video. Even though there's not smoke, you can just smell it. And then here, I remove it. You see how the voltage jumps right there. I actually have removed the connector completely such that it has probably broken connectivity, so there's no more production happening on that string. It hasn't tripped the arc fault yet. It is going to in a minute. But we keep going. I'm keep wiggling it. And then right about there, you see the voltage starting to come down. The voltage comes down a little bit from open circuit voltage when it starts producing. When you start getting amperage from it, the voltage comes down, the amperage comes up. So yeah, so the voltage is coming down and then it goes back up. The arc fault's triggered, and this is where we are at, and so is the end of the video. So the things that we have learned that are helpful are we can totally simulate an arc fault situation with my setup here that does actually trigger the inverter's arc fault interrupter, and pretty reliably too. The second time didn't go as fast, but it did still go in a reasonable time. If you keep messing with it, it's going to trigger. The second thing we've learned is that an oscilloscope with just a screen like this without the ability to go deeper into the information is not going to be adequate for what we need to see really anything that is happening when an arc fault's triggered. Not saying that an oscilloscope is not going to be useful at all. I think it still will be, but we need that logging functionality to be able to bring it back and expand everything, look through a bunch of parameters bit by bit, and compare with, what was, maybe timestamp it super specifically so that we can compare between the video and where it is at in the logger. I have access to a more capable power quality analyzer, and now that I've done this, I feel like I can do this again another time. Maybe we'll get some interesting results. But one thing's for certain, there's a lot of controversy when it comes to arc faults in the electrical industry in general. For AC coupled systems, they have not been proven to actually reduce the number of fires, the number of electrical fires that happen. And they cause a lot of nuisance trips. And it's not like we don't have nuisance trips in the solar industry, but I do think probably DC arc faults are a little bit different. I don't know how rapid shutdown, like power line communications, factors into all that. I'm sure that makes that all complicated. This is on a non-power line communication system. There's no rapid shutdowns, no optimizers. It is just pure solar DC with the inverter manipulating the voltage amperage. So this is pretty straight up, and clearly you create an arc fault and it trips. And I have definitely had arc faults that have tripped that have been because of bad connectors. I am more a believer in arc faults now than I probably was before this video. But at the same time, we still need to be able to figure out why these arc faults trip. Because as far as I know, nobody shares their data on their algorithms for arc faults so that we can have tools to analyze faulty arc faults, so instead of coming to a site that is an hour and a half away constantly to switch around wires until we can kind of isolate, okay, which is the string that is bad. This is the problem that we need to solve in the tool industry. We need some sort of arc fault detection tool. Hopefully this will be helpful, interesting to a number of you, and thank you for supporting the channel. I will be striving to upload more regularly, and I'm gearing up to have a great end to the summer here. So we'll see you next time.